So you I think you believe that this, you say, I can then write, you see, the 1 over n is the probability of selection. Also, 1 over n over here, x2, and so forth. Okay, till we get to 1 over xn. So these are probabilities, right? Because if I have a sample of n, the probability that I select each of them is 1 over n, right? Okay, so it means that I can do this, okay, as the probability of selecting xi times xi, okay. But because I'm summing all this, I need to sum, right? So I need to sum as equal to the sum of I moving 1 to n probability of x times x. Please, do you all agree? And this probability of 1 over n, is everybody okay? Therefore, I can write expectation, okay? As I said, the expectation is just like the variance, the mean that we are using this to now be able to define what we mean by mathematical expectation. So the expected value of the random variable x, the expected value expected. So we say that the expected value of x, and this x is a random variable, is defined from please mute them for me. If you want to ask a question, you yourself. Okay. So the expectation of x, or the expected value of x, is defined as this: e of x, and here we are using the random variable x, right? It's the same as 4x, okay, x times okay. So I can even write this better, and doing this doesn't confuse you. So we are saying that when writing it in full like this. Okay. So that's it. Remember that this is for what? Discrete random variable. So I can also have what? A continuous random variable. In that case, if we have this, a continuous case, it will be what?
The integral.
The integral. Good. So it will be the integral across all x. What? X times what? F of x dx. Is everybody okay? So the mean that you were finding SHS up to level 100, okay, we can express it in the probability form. That's what we are trying to do now. Okay, so let's take an example. So the first example, we go back to the toss of a coin, right? Toss a coin twice. So example, we toss a coin or toss a coin twice. Okay, what we know the distribution, right? The distribution of discrete, we'll be using this example over and over again. So I can write it here. It's like that. We have x, and then we have the probability, right, of x. So 0, we have 1 over 4. 1, we have what? 2 over 4. Sorry. we have what? 2/4, and then 2, we have what? 1/4. Do you all agree with it? It's okay. So if we want to find the expected value of x, by definition, the expected value of x will be what? X, and look at the way I'm writing. So the small x are values, right? Okay. So in our case, this will then be what? X will move from 0 to what? 2. Is everybody okay? X, P, X is equal to what? X, like that. Okay. So in this case, when x is equal to 0, we have what? 0 times what? 1/4 plus x is equal to 1. What is its probability? 2/4 plus when x is equal to 2, what is its probability? 1/4. So we find this, at the end of the day, we should get what? Oh, okay. Broken line. Okay, so we get what? This will be 0, this will be what? Half, then we have what? 0,
1.
we have what? 1. Is everybody okay?
Yes, sir.
Yes,
So that's the expectation. Okay. Now let's look at the case of the continuous case. So the example we did, f of x is equal to, so 2, example 2 is a continuous case, right? So in the continuous case, let's take our example from the previous our previous example. F of x is equal to what? The example we've been using, 1/9x, right?
1/9 squared.
Good. Okay. So it is 1/9x squared, and x is between what? 0 and then 0 squared. Okay. So here, by definition, the expected value of x will be the integral for x of f of x dx. Okay. So in our case, and remember, if I write all x, it is also equal to the integral from negative infinity to positive infinity, x, fx, x. That's what I mean. Is that okay? So in the discrete case, it means s takes from negative infinity up to positive infinity. Please take note of that. In some books, you may, or when we examine, you will use that. It's not different. Okay. So in our case, the integral will be from what? 0 to 3, right? Is that okay? X, fx, dx. Is everybody okay? Now,
Yes, sir.
this
Yes,
one, it means that we move from 0 to 3, x times what? 1/9 squared dx. Is that okay? Then we're going to have what? 0 to 3, 1/9 s dx. So we integrate that one. If you integrate, what will you? Can you do so quickly? Provide me with the answer.
9.
So you get what? 1/9. You integrate that one, you get x. So times 4, right? Isn't it? The next power for 0 to 3. Right? Is everybody okay?
Yes, please.
Yes, sir.
Then we put
Yes,
10
sir.
in. So at the end of the day, we get what?
9/4.
9/4. Okay. So that's the expectation of that value. So is everybody okay with what expectation? This fit is continuous. If you are not okay,
Yes, sir.
Yes, sir.
ask you down to 8. Okay. Next, we talk about properties of the expectation. Now, so our properties, yeah, properties of expectation. Now, from the definition, what do you, if A is constant, what do you think will be the expectation of A?
That constant. 0.
Why? Yes. Why?
Because when you integrate a constant, you get 0.
When you integrate a constant, what do you
Yes.
You get that constant, but the reasoning is all right. So let's look at properties. Properties. Okay. So A. So 1. If A is a constant, if A is a constant, so it's difficult for me to write, but of course I'm saying it. Get the video. Even now, you understand what I mean. Okay. So let's bear with me, but it's a bit too right on the screen. So if A the expected value of A is the same as A. Is everybody okay with it? Now we will prove this. The proof is this. And you can use that continuous case or discrete case. Let's take continuous. Okay. Third value of A is the same as boy. If I have A, third value of A, okay. Remember, when you take integral, you take the value that it takes. So it will be A, right? F of X, dx. Okay. Now, so this one, A is a constant, so I can bring it outside the bracket. Then I have F of X dx. What is this one? If we integrate across
1.
1, good. Okay, so it means that this is equal to A. Is that okay? So that's the proof. You can as well use a discrete case as an exercise. Okay. All right. Okay. So we can move to 2. Any question on this before I move on? So next, 2. 2. So A is a constant and X is a random variable. A is a constant and A is a constant and X is a random. Then what happens? Expected value of AX is the same. From what we have done, can you tell me what this will be?
So will be equal to A
Times the expected value. Okay, good. How do we prove this? So proof. Okay. Now, by definition, the expected value of X is equal to what? X fx dx. Right? Okay. Now, so if we have the expected value of AX, then we expect it to be the integral AX, sorry, A, AX dx. Do you agree? Do you agree?
Yes, sir.
Yes, please.
Fx dx. Now, because A is a constant, we can bring it inside the integral. Then we have this. And what is this? What is this?
Expectation of
It's the same as the expectation of it, right? Okay. So it means that we get to A expected value. Okay. So three. Any question? Three. A, B are constant. A, B are constant. X is a random variable. Then can you tell me what will be the expectation of this? From what we have done from 1 and 2, what is the expected value of this?
that will give us
It will be
expected value of A plus B expected value of X.
good. Okay. And from those two proofs that we have done, you can prove this as well. Okay. All right. Let me move on. 4. 4. So I'm continuing from 3. Y is also a random variable. Then what will be the expected of this? What will be the from what we have done? So A
A
yes, plus what B expected value. Good. Is everybody okay?
yes, sir.
What it means is that we can give you a combination of the linear of the variables for you to yes. Okay. Next, I talk about variance. So remember that all this, the previous one we did, I can't ask you to find the expectation of, let's say, 2 times x or whatever. And if you use this principle, you should be able to do that. Okay. Next is now the variance of The random variable x defined as you see, yeah. So I have to start from your what you know already, which is from your SS and also level 100. Okay. Now, how do you find variance? The sample variance, S squared. How do you find this? You do 1 over n minus 1, isn't it? Plus sigma x minus all squared. You all know this, right?
Yeah.
Good. Okay. Now, why do we divide by n minus 1 and not n?
Because it is a sample.
Because it is a sample. Yes, I said it's sample variance, so I know it's a sample.
Because you want to leave room for error.
You want to make room for error. Okay. You said something. Who else? This deals with what we call degrees of freedom, right? So before we estimate the variance, we use one of our degrees of freedom in estimating the mean. Is that okay? The S bar we did over here. Okay. Now it's simple. Okay, so let's say, the concept of degrees of freedom, let me just explain it. Degrees of freedom. So I am assuming I call 3 of you, right? Okay. Who is monitoring for me? How many people do we have in this class?
43.
We have 39.
43.
39,
43.
44.
Now it's
44
44.
now.
It's 45 now.
44. Okay. Is it
It's
that
45.
most of you did not know, or they are enjoying their Saturday night?
So please, others have just posted in the class group that they're having problem with their network.
Okay, all right. But we are recording, so I hope to make the recording available. But it is good when whatever we say, I can record them. And then when I'm teaching, I'll say it is available rather than recording the video. But okay. So let's continue. So please listen to me. For you to understand some of these things, I have 3 people from this class. So I asked you of your ages. The one said 18. Yesterday, somebody said 20. I didn't believe it. There's some. Are you here?
Yes, sir.
You are not the one I asked of your age. Okay, so okay, so let's go. So I'm saying that the total age, okay, and I'm giving you the 2 people. Their ages are 18 and 20. Can you tell me the age of the last person?
22.
22. Good. Okay. So if I
Yes,
say
sir.
23, will this be correct?
No, sir.
No. Good. Okay. Okay. So now, please listen carefully. Okay. So now, I only tell you the. Oh, somebody is just making noise. I only tell you the age of one of them. But I tell you that all the 3, their ages are 60. Can you tell me the ages of the 2 people?
No.
Oh, you can't tell me.
Yeah, we can.
Yeah, you can say something. That will make this relation correct. I can say that one is 1 year old, the other is what? 39. That sums up to 60, isn't it? Is that not it?
Yes.
Yes. I can also say the remaining 2 are all 20 years. That also satisfies it, right?
Yes, please.
Yes, so we will have a whole lot of numbers that will satisfy this relation. Okay. Now, so it means that when I put 18 here, I restrict your freedom. Is that okay? Of movement.
Yes, sir.
Good. Okay, so that's the concept of degrees of freedom. Okay. And in statistics, we use it a lot, but you can use this simple analogy to understand what we mean by degrees of freedom. Okay. All right. Okay. Let's move on. I should say that when you do statistical invariance and do multiple likelihood, you also have another one which is x bar squared like this. This is also an estimate for the variance. Okay. This is also an estimate for the variance, but I think we will do this in your statistical invariance. So as of now, this is what you know, isn't it? The sample. This is also very simple as well. Yeah, so let's just use this. Okay. So essentially, if you look at the way I derive the expectation, it is the same concept I can use over here, right? Now, what will happen is that I can find the probability of each of them, right? So I can rewrite this as 1 over all, n minus 1. Remember, we have all the degrees of freedom, right? So this will be x 1 minus all, s bar all squared, plus 1 over n minus 1, x2 minus s bar all squared. So I'll do this until I get to the last one. Is everybody okay? Is everybody okay?
Yes, sir.
Good. Okay. Now, which means this is the probability, right? This is the probability. Now, this one, we can also write this as an expectation, right? Do you agree? The mean, remember I use the same concept in doing it. Okay, so essentially, let me say intuitively, I can now say that the expected, the variance of x is the same as the expected value of x minus its expected value all squared. Because this one too, I can say it's a station. I have a p times what? Some x, which is the square deviation. Okay, so this is what we call the variance. The expected value of what? The difference, which is what you see over here, right? All square. Okay. Now I'll leave this as an exercise. Okay. So I can expand this. If I expand this, maybe I can do so. This will be expected value. I'll get what? S squared minus what? X, expected value of x. Okay. X times the expected value of x, and then I have okay. So essentially, you have what? A minus b all squared. What is this one equal to?
A
squared
plus B squared.
squared minus 2ab
Minus 2ab. Yes.
plus b
Plus b squared. That's the same thing I'm trying to do over here. Right. So we can do so. Let me write this more in small. I can write it over. Okay. So we'll get s squared minus 2x value of x plus expected value of x all squared. Do you agree? It's the same as that one. Is that okay? Then now I can
Yes, sir.
find my expectation.
Yes, sir.
So this will be what? Expected value of x minus the expected value of x, b is a constant, right? But x is not a constant.
Yeah.
Yeah, so I'm going to get minus expected value of x times expected value of x. So it will be expected value of x all squared, right? Plus what? Expected value of x all squared. Is everybody okay? All right. Okay.
Yes, please.
Now, it means that I can now subtract this. So essentially, I'll get expected value of x squared minus expected value of x all squared.
Oh,
That's the variance. Is that okay?
yes, please.
Good. Okay. Right. So now we can talk about, let me talk about the properties before we take an example of the variance. Now, so let's look at this. If A is, so we are doing the same, so I'm not going to write, but if you do one, so properties, right? What is variance of A? By definition, variance is equal to this, right? So if I have variance of A,
Yes.
wherever I see X, I'll put A over there, right? So I'll have the
Yes.
expected value of A squared minus what? Expected value of A all squared. Do you agree?
Yes, please.
Good.
Yes, sir.
Okay.
Yes, please.
Now let's see what happens. The expected value of A squared is what? Remember what we discussed on
It's
computation.
A squared.
Good. It's A
It's A
squared.
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 Good. Then expected value of A within here will be what?
A.
A.
Good. And then we
A.
have the square. So it becomes A squared.
A
So
squared.
A squared minus A squared.
0.
Good. Okay.
Zero.
The variance of a constant is what? Is 0. And this you get it from your basic statistics. If I say that I ask of your ages and everybody in this class is 18 years, what is the variance for your ages?
0.
It's 0. Do you get it? It's the same thing because if I ask what is the ages of these students, I'll just say 20. Right? Everybody is 20 years. So variance is so this is also correct. Okay. Now let's look at the second one. We are using the same thing what we use for the expectation. So that's why I'm not writing all again, right? So what about variance of AX? So by definition, we are going to say this expected value of what? AX all squared, right? Everything there squared minus expected value of AX all
Oh,
squared. Is everybody okay?
yes, please.
Good. Now
Yes, sir.
we now go over here and say that the expected value of AX squared, it means A is a constant, so I can bring it outside, right? And say
Yes, sir.
AX squared. Do you agree?
Yes, please.
Yes, sir.
Yes,
What
sir.
we have discussed. Then minus this one, so I bring it out, I square it, it will also be A squared, right? Expected value of X
Yes.
Yeah.
all
Yes.
squared,
Yes, sir.
right? So therefore, I can bring A outside this. I have just expected value of X squared minus expected value of X all squared. Right. Okay. So from this, I can conclude that this is A squared variance of what? X.
X.
Are we okay?
Yes, please.
Any question, please?
Yes, we are.
Okay. Then,
Sir, please go over
No,
the
sir.
part again.
which part? Okay, so let me just track back. Remember that from definition, we are using the definition. Let me write this one properly. We are using the definition. So if you know the definition of variance, right? So if I have whatever, let me track this again. Remember the variance is this, right? You remember this? This one. Okay, so that's what we are doing. Variance of x equals expected value of x squared minus expected value of x all squared. So if I come over here, within the variance I have ax. So what am I going to put over here? Definitely I'm going to put ax all squared, right? Okay. Then
Yes,
to
sir.
be a squared, but a is a constant, so I can bring it outside the expectation side. Remember what we did for expectation, the property. Then this one too is a constant, so it comes out of the expectation side. But we have squared over here, so right here, you square it as well. Okay, that's why we have this. Then I have a squared. I can factorize it out. Get that? What is this expression? That's the definition of variance. That's it. That's difficult. Okay. Let me look at the 3, unless we have another question. So the third one will be variance of A plus B. What would this one be?
The variance A plus B times the variance of X.
A plus B times the
Yes, please.
please.
B square variance of
Good.
B square variance of
It
X.
will be B variance of X. Everybody
X.
okay? Remember, variance of a
Yes, sir.
constant is 0.
Yes,
Variance of dx is like variance of a just that we just did up here. So that would be b squared variance of. Okay. Now, what will be the variance of negative 3x? Variance of negative 3x.
9
9
variance of X.
9
9
variance of
times the
x.
variance of
Good. Okay. So we are getting somewhere. And then lastly, 4. Variance of ax. I'm going to put bx. Can you help me do this? The first one will
Yes,
be what?
please. A square
Variance of X.
Variance of X
variance of X plus or minus
Here.
B square variance of X.
Minus or plus.
No. No.
No, it
Plus.
should be only
It
plus.
should
Plus.
be plus because whatever it is, he said it should be b squared variance of x. The variance of it should be y squared. Wait, I put y. So x and y. X and y variables. Then actually this will be plus or minus 2ab Plus or minus 2AB. The covariance. Do you remember covariance? You know covariance.
No, sir. No, sir.
No, please.
Correlation.
Yes.
You know the Spearman correlation coefficient.
Yes, please.
Good. Then
Yes.
you know.
Yes.
How do you find out? You divide the covariance. What you were finding as nxy minus sigma x sigma y. That's the covariance, right? Of course, you divide by n minus n minus 1. Is that okay? So that's it. And remember, the covariance is the same as what? The rho times what? Sigma x, sigma y, right? This is the equation of the covariance, which is sorry, the covariance of 1 and 2. So essentially, we can write this as also, if I put it below here, as plus or minus 2AB rho sigma x sigma y. It's the same. Now, we usually make use of this if x and y are independent. If they are independent, two variables are independent. What is the covariance? Or what is the correlation between x and y if x and y are independent? Please, I have two variables. They are independent. They are not related, right? If they are not related, what is the covariance or what is the correlation? The correlation is what? Is zero. Is zero, right?
Zero.
Yes. So this whole part will not be there. This part will not be there if x and y are independent. Okay. Now, this thing, it has application in finance when they want to construct a portfolio. You know, a portfolio is a collection of what? Assets, right? So in the tree language, they will tell you that we have this proverb that you don't put all your eggs in one basket, right? Okay. So when you are investing, you see, if you invest and the X and Y are different stocks, then it means that if they are positively related, you will get a high what? Risk or variance, because you are going to add 2AB covariance to whatever you have computed over here. But if they are independent, you have only this part. If they are negatively correlated, then you have negative over here. So you end up what? Taking something from this independent part, which will minimize the error. So in other words, when you are investing, you invest in what? Stocks that have in which their prices move in opposite direction. Or if something happens in in 2018 or so, they collapsed so many banks, right? You see, so if you have investment in the banking sector alone, you will tend to lose. So, but if you diversify and you have some in, let's say, manufacturing companies and all the other things, some will go up, others will go down, so they balance out. So that's what we mean. And this correlation and variance plays an important role in such decisions. So I'm just bringing this to your attention so that when you are doing this, you know the essence of it, right? In real life situation. So that's it with expectation and variance. Any question? So when you take a random variable, you should be able to what? Calculate the variance by finding what the expected value of x, then the expected value of x squared. Okay, the expected value of x squared is not that difficult. We've done some. Just do one, just to make sure that people are understanding what we did. So remember that the toss of the coin, we've done. We know the expectation. The expectation is one, right? Okay. So if we want the variance of x is going to be expected value of x minus expected value of x. Just a moment. X squared minus expected value of x all squared. Okay. But we know this one to be 1. What we don't know is this. By definition, the expected value of x is the same as, in this case, s times the probability that x is equal to x. Is everybody okay? So I go to, this is x, I go to the table, right? And then I find x. When x is equal to 0, what is the probability? So 0 squared times
1/4.
1/4 plus 1 squared times what? 1/2 plus 2 squared 1/4. So please take, it is not the probability we are squaring by what? The random variable. The values of the random variable. So this is 0, this one we get what? Half, this we get what? 1. So essentially we have what? 3/2. Is that okay? Is it okay?
Yes, thank you.
Good.
Okay. Yes, please.
Yes. But we
Yes,
are
sir.
not done, right? We now have to find the variance. The variance of x. Remember, the variance is on the random variable, not the value the random variable takes. The value the random variable takes is equal to what? The variance is equal to 0 because it's a constant. So please take note of that. Good. Okay. So we're going to get what? The expected value of x squared is what? 3/2 minus what? 1 squared. Is everybody okay? Because the expected value of x was what? 1. So we can find this to be what? Oh. So we find that to be what?
Half.
1/2. Okay, please. You have to switch off your please, can you see my screen?
Yes, please.
You can still see it.
Yes.
So we get what? Those with their videos on, please take it switch it off. So you say you get what? 1/2.
Yes, please.
That's the variance. Okay. So the variance is 1/2. From variance, we get standard deviation. What is the standard deviation? Square root of what? The variance.
Half.
Yeah.
So we can find the Standard deviation as well. And that means we have what? Square root half. So that's the standard deviation. Is everybody okay? So I leave
Yeah.
the continuous case one as what? As an exercise for you. Find the variance. You can multiply it by a number and find the variance and so forth. Are we okay? And then you can do tutorials on it this Wednesday as well. Okay. Is everybody okay?
Yes,
Yes,
please.
please.
Can I move on now? Can I move on?
Yes, please.
Okay. Now I want to talk about some distributions. So you see, we've been talking about random variables. Okay. Now, because I can observe several phenomena in life, it is important that we can characterize random variables so that we may have some distributions for it. Okay. And when we have known distributions, it becomes easier so that if you are in Ghana or you are in Russia and you encounter the same analogy, you can now describe it um, with some characterizations. Now, because of that, there are several distributions that people have studied and named them. So we're going to take a look at some of them. Okay. Now, maybe I can go to your slides and um, and show you some of them. I'll mention them because you may not have them in the slides. Let me maybe when stop sharing. Okay, then share again. Okay, yeah. Do you see the slide?
Yes, please.
Good. Okay, so this one you have it
Please.
already. So now remember that we talked about what? Discrete and continuous distribution. Okay. So if you have a discrete random variable, okay, that results in two possible outcomes which are mutually exclusive. Then we can characterize it as a Bernoulli distribution. Okay. So for example, when we play, there's a football match, the referee. Hello. Yes. Good evening. Debbie. Ẹnyẹ hwee, ẹyẹ wei drinks ne I'm sending books no. Ẹpẹ, Monday, ẹnyẹ hwee, yo, no. Baby, answer any. Yeah. Okay, all right. Okay, thank you. Goodbye. Okay, sorry about that. Let me see. Okay, so when I have experiment like in the football match, you throw the coin. A coin will have a head or a tail, right? Or the meteorological services will tell you that maybe it will rain today. So what are the outcomes? It either rains or not, right? I asked you a question whether you will vote in the next election. You either answer what, yes or no. So if you have a variable that takes on two possible outcomes or an experiment that results in two possible outcomes where they are mutually exclusive. That is, you cannot be what? You cannot be here and there at the same time. So we classify our sex as what? Male or female. So I expect that when I come to the class, I will see either a male or a female. Then that's what we mean by a Bernoulli distribution or a Bernoulli process. Is everybody okay with this?
Yes, please.
Good. Okay. Now,
Yes, Lord.
so for a Bernoulli trial, it results in two possible outcomes. The outcomes should be mutually exclusive. Okay. Mutually exclusive means they cannot occur, together, or you cannot be here and there at the same time. Okay. Now, so we also say that the probability of success, okay, is P, right? So the probability of success is P. If I'm repeating the experiment, it will remain the same. Okay. Now, so if you have a distribution like that, we call it a Bernoulli. And this is how you write a Bernoulli. Okay. It is not difficult or how to get it. I can rewrite it for you to see how that is done. Okay, so let me go back to the whiteboard. Please, do you see the whiteboard?
No, sir.
No. Okay. Remind me, I'll get you a book that makes these ones quite easy to read. Professor Nelman's book. I'll get a soft copy and send it to you so that you can read about that as well. Okay, so essentially, the probability, now you can see this, right? Okay.
No, Doc.
You can see the whiteboard.
No, please. We can't see the white.
You only see that part.
Oh,
You are seeing the audio report.
you are seeing what?
The audio.
Do you see anything now?
No.
Good, okay. Because I have stopped sharing. You must see the whiteboard now.
Yes.
Good.
Yes, we
Yes,
can
please.
see.
Good. All right. So what I'm saying is that here you have two possible outcomes, right? So let me assume that I toss a die, right? And the die, I want to get a 6, right? So I can write it as this, that the probability that s is equal to x is 6 will be what? 1/6
1.
if 6 occurs, right? Okay. That's
Okay,
my
sir.
surface. Then what will be the complement of this? It will be
5/6.
Yes.
5/6.
Otherwise. Okay. So this is what they are putting together. So it's what is this is P. So alternatively, I can write this as what? P. Okay. P if X occurs. What I'm interested in, okay, and it is what? 1 minus P if what? It doesn't occur. Something like that. Okay. Now, it is the same thing that you're going to write in the formula what they have written in the slide. Okay. So if you understand it from this point of view, then I can put them together that the probability that x is equal to x will be the same as p to the power x and then 1 minus p, 1 minus x, and x is equal to 0 or 1. So when x is equal to 0, what happens? It is what? 1 minus p. That is, it doesn't occur. If x is equal to 1, it means it occurs. I get p. So you see, this will result in what we have intuitively derived over there. Is everybody okay?
Yes, sir.
Good. All right. So now I can go back to the slide. Oh. I'm still. You still see the slides, right? No, the. Good. Okay. So there it is. Okay. So that's what you have over here, right? Please, can you see it?
Yes, please, we
Good.
can.
Okay.
Yes.
So that's the
Yes.
probability. Of course, your P is the probability of success, so it should be between 0 and 1. Now, the expectation of x is equal to P. The variance of x is P, 1 minus P. It is easy to prove this from what we have done. That's why I started from that. Okay? And maybe I should just do the expectation, and all the rest I will not do it. That's why I took my time to go through that one so that you understand it and you can apply it. So at any point in time when we are doing something and you don't understand, please make sure you ask, okay?
Okay.
We want to do this. Share. Good. Okay. Now let's look at this one. We want to find the expectation. So the expected value of x, the expected value of x, you know, by definition, this is a discrete distribution, right? So we expect it by definition, the expected value of x will be x
X times P of
Is everybody okay? Now, for the Bernoulli, this will be that we sum x from 0 to 1. Is everybody okay? P, x, P, 1 minus P, 1 minus X. Is everybody okay?
Yes, sir.
Good. Right. So now I can write this as well. When x is equal to 0, what will happen to all this? It will be 0. 0 times whatever will get 0. Plus 1 times what? P, 1 minus P, 1 minus 1. This part will be what? 0. we are left with what?
0.
P. Is everybody okay?
Yes.
Good. Okay. So
Yes,
the
please.
expected
Yes, sir,
value
we
of
are
X is
okay.
P. And that is what you see in the slide. Is everybody okay? Now, we can also
Yes,
look
sir.
at the variance.
Oh, I see.
Variance of X, the expected value of X squared minus the expected value of X all squared. We know expected value of X already. What we don't know is expected value of X squared. Let's quickly find it. The expected value of X by definition is S squared the X is equal to X, right? So in our case, that means X starts from 0 to 1, S squared times what? Px 1 minus P 1 minus X. Is everybody okay?
Yes, sir. Yes, sir.
Good. Now this will be equal to, when X is equal to 0, what happens? Everything will be 0.
It will be equal to 0.
Good. Plus,
0.
when X is
Yes.
equal to 1, we'll have 1 squared times what? P. The other one will be what? 1.
P.
This will be 0. So it's 1, right? So what do we get?
Yes.
Expected value of S squared is equal to what?
P.
P.
It's P.
Yes, sir.
Good. So you realize that expected value of S is equal to P. Expected value of S squared is also equal to what? P. So what is our variance? Variance of
Variance is
S
equal to P.
equal to S squared minus what? Expected value of S all squared. This then will be equal to what? P minus P minus what?
P squared.
P squared.
P squared.
P squared. Which is the same thing. If we factorize P out, we get P 1
P
minus.
into bracket
We
1 minus.
usually will write this as equal to P where Q is equal to 1 minus P. Okay. So if you go to the slide, this is what you see over there that has been done like that. So it's what we have gone through. Now you should be in a position to understand the subsequent distributions we are going to talk about. It means you can start, deriving it from what? From basic principles, from the definition of what? Variance. So this is what you are seeing over here. And that's how you derive it. Is everybody okay?
Yes, sir.
Good.
Yes, sir.
Okay. So now, can you continue with, I'm asking you, I said we toss a die. Our interest is in getting a 6, right? What is the expectation?
1/6.
The expected value is 1/6. What is the standard deviation? What is the standard deviation?
1.
The standard deviation is 1. I doubt.
Root 5 over 6.
It was
Root 5/6.
root 5/6. Okay.
Root 5/6.
Okay. All right. So this one, find the distribution of W. This you should be able to find it, right? And then find the expectation and variance. So the example, you should be able to do it in the book. It's just like we have discussed. Okay. So like that. P is that, and so forth. So it's quite easy for you to do this. Okay. Now I'll discuss this and then we close. Okay. So a binomial distribution. So the binomial distribution is just a collection of Bernoulli trials. Okay. So I may say that I want to toss a coin 10 times, and then I want to see the number of times head occurs. Okay. So what is the possible values of x? A head may not occur, which means 0, right? If one head occurs, x is what? 1. If two heads occurs, what happens?
X is 2.
X is 2. So it means x can move from what to what?
0 to 2. From 1.
No. From what? 1, not only 1.
0 to 2. 0
What?
to 2.
0 to?
0 to 2.
No. If I
2.
toss the coin 10 times, what are the possible values of x?
0.
0,
0
yes.
to n.
0 to 10. Good. It should be 0 to 10. Okay. So a binomial distribution has some characteristics. Okay. And those are the characteristics you have over here. That the experiment consists of what? N independent identical trials. Right? So I perform the coin, I toss it 10 times. My N is 10, right? The way I toss it should be the same way, right? It should be identical, okay? And then also independent. If we say independent, my first trial should not have any effect on my second trial. So, and then each trial results in two possible outcomes. That's why we say it's a collection of what? Bernoulli processes or Bernoulli trials, okay? Then the probability of success in each trial is P, and it remains constant throughout the trial. Why is it so? If I'm using a coin and the coin is fair, it should be the probability that I get a head is half, so it should be half for each trial that I do. Okay. Now here the random variable of interest is or the number of successes observed during the end trials. That's why I was saying that if I'm interested in getting a head, then out of the 10 times there's a possibility that I get no head, I get 1 head, 2 heads, up to 10 heads. Okay. And what else? So that's it. If a random variable have these properties, we can term the distribution as what? A binomial distribution. Now, the binomial distribution, okay, is the probability is this. There is a typo here, so we need to correct it. Okay, so from what we have done, you should know that this is wrong, right? Who can tell us why this is wrong? Who can try? The exact thing we should put over there is what? X, capital S is equal to
Capital X is equal to X.
Small x.
Small x.
good. Okay. So that's
I'm
it.
confined to a better small x.
Good. Okay.
Yeah, the sum before it has to be after x or small x.
Good. Okay. All right. Now,
Ah.
you see, this one I can derive it intuitively, right? So that you understand. Now, remember, I said. So let me just use this place to. I said I tossed the coin 10 times, right? So what will happen is that I can get head, 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 and so forth to what? Maybe tail. If I get head, my x is equal to what? 10, right? Now, so if I'm doing it n times, then if I get a head, that is p, right? Success, p, and p, and so forth to some p. Then I can get kill, failure, up to what? Kill. So it means that from what we have done, x is the number of successes, so x will be this. But the number of x plus the number of failures will give us what? N. So this part will be what? N minus x. And together we get what? N. So out of this N, I have what? X successes and N minus x failures. Is everybody okay?
Yes, please.
Good. Okay.
No.
Oh, I said I tossed the coin, let's say 10 times, which is my N is equal to 10. And X is the number of successes, which is the number of times heads shows up. So what will be the number of failures? What will be the number of failures?
1 minus
Not 1, but N minus X.
N minus x.
Good. Okay. N minus X. Now, is everybody okay? Now, what is happening is that because I have P, and I am saying that they are independent, what is the probability of their joint occurrence? If two events are independent, what is the probability of their joint occurring?
0.
Not 0.
0.
No.
1.
No. If A and B are independent, what is the probability of their joint occurring?
Probability of A times probability of B.
Good. Probability of A times probability of what? B. So that's the concept we are using over here. I think what you were telling me was the mutually exclusive, but that's not what we are after. Okay. So what it means is that the probabilities, what I have over there, I can what? Multiply them. So if I have P x times and I'm multiplying it, what will be the outcome? So this is part of what? Px, right? Because they are the same. What about the K? It will be K what? N to the power x. Is everybody okay?
Yes, sir.
Good. So this part is what you see over here. Is that okay? Good. Then someone will ask, what about this one? The N combination X. Well, you see, if I throw, it is possible that, where's my head? This one, right? If I have a tail over here, it is possible that I'll get the tail happening first, or the tail at the middle, or the tail at the end, and so forth. So the number of ways in which we can have X occurring out of the N is this one. So I can get P. I can move it to the other side of here, or all the P's can come here, okay? Or one Q can come to the front, and so forth. So you can have different ways of arrangement or how the successes occurs within the N trials. And that is catered for by N minus A. So intuitively, that's how you derive the binomial distribution. And X, remember, is the number of successes. So you start from 0, 1, 2, 3, up to N. Please check the domains of all the X's that we'll be dealing with. Okay. Now, because the binomial distribution is what a combination of the or a collection of what Bernoulli trials and Bernoulli trials, then the expected value of S is what? NP. And the variance is what? NPQ or NP1 minus P. Remember, it's just what? Multiplying the number of trials by the expectation and also the number of trials by what? The variance. And you get that of what? The binomial. So with this, I think you can go through the examples that is in the slides, and then you can work some more examples when you meet for your tutorials. Is that okay?
Yes, sir.
All right.
Yes.
Any question? Other than that, we close now.
No, sir.
Okay. All right. So hopefully during the week we will have one more online course a class like this in the evenings so that we can catch up with some of these distributions. Okay. All right.
When are you coming here?
Can do it every week.
We can do
What
it
every week? Can you do it every week?
You can do it
We
every
can
day.
have it every week.
every
Every day.
every day.
You can't have it
Yeah.
every week.
Every day.
If you do it every day,
So
it will be like the
every
cookathon they are doing. You
Yeah. We said every day. It's every day.
it will be a cookathon, and then nobody
We
will
learn
like
that
to listen to you anymore.
This one we learn that one.
This one is one. Okay.